In this video, we are going to look at the acid-base dissociation equations worksheet. And so on this sheet it says to go through and label the acid and the base, and if possible, label the conjugate acid and conjugate base. And then finally, we're going to highlight the species that affects the pH of the solution. And so let's just start with number 1. Remember, water is a special kind of compound. It's called an amphoteric compound. And that means that it can behave as either an acid or a base. And so in all of these problems, one of the species that we're looking at is water. And so we really need to look at the other substance to determine whether water will act as an acid or a base. So looking at this first one, we know water can be either an acid or a base, but looking at HCl, we know that this is hydrochloric acid because it starts with hydrogen. So we know that this species is going to behave as the acid. So I'm going to label that acid, and I'm going to label water as the base. And then we know that a Bronsted-Lowry acid is going to be a proton donor. So it's going to donate a hydrogen to the water. So HCl is going to give up its hydrogen and just be left with Cl-, and then when it donates that hydrogen to the water molecule, we can kind of put an arrow showing that it's moving over here. Now we end up with H3O, and because there's an extra hydrogen, we are going to end up with a positive charge. So now we've labeled our acid and our base, we have written our two products on the other side of this equation. Now we just need to label the conjugate acid and conjugate base. And so looking at this side of the equation, whichever species was the acid is going to end up being the conjugate base on the other side, and whichever species is the base is going to end up being the conjugate acid. And this is because it's now a species that could act as an acid. So H3O plus has an extra hydrogen. It could donate that hydrogen to the Cl-, so now it's going to act as an acid. The H3O plus would act as an acid, so this is the conjugate acid. And I'm just going to abbreviate them Ca, which leaves Cl- to be the conjugate base because it could receive the hydrogen donated by the H3O plus. And then finally, we need to label the species that's going to affect the pH. And we know that the things that affect the pH are OH-, H+, or H3O+ ions. And so I'm going to box in the H3O+, highlighting that that is the species that will affect our pH. Moving on to number 2, we have NH3 plus H2O. So our water, once again, is amphoteric. It can behave as an acid or a base, so we need to decide whether NH3 is an acid or a base. NH3 is ammonia, which is a common base. It's one that's just good to memorize off the top of your head and know that. But really anything that contains nitrogen, an organic molecule that contains nitrogen, which this isn't an organic molecule, it doesn't contain carbon, but there are oftentimes organic molecules, carbon-containing compounds that have nitrogen in them, and those will also act as bases. But NH3, this is the ammonia molecule, and this is always going to act as a base. So because NH3 is going to act as the base, water is going to act as the acid in this case. So because water is acting as an acid, the acid is going to be the proton donor and the base will be the proton acceptor. So water is going to donate a proton. We're going to be left with just OH. And then OH is going to have a negative charge because it lost a positively charged hydrogen. And then the NH3, the base, is going to gain that proton. So we're now going to have NH4, and because it gained an extra positive charge, it will have a positive charge overall. So now we need to decide which one's our conjugate acid, which one is our conjugate base. And so NH4 now would have an extra proton to donate, so this can now behave as the acid, so I'm going to label it conjugate acid, and then OH- could receive that proton, making it the conjugate base. And then finally, we need to highlight the species that's contributing to our pH value. And so that would be our OH minus. Contributes to the overall pH of our solution. And I just want to draw your attention to the fact that although NH3 doesn't look like a base, first looking at it, it doesn't have an OH in it, this OH minus that's produced through the reaction of NH3 and water is the reason that NH3 does behave as a base. And so while all Bronsted-Lowry acids are also Arrhenius acids, Bronsted-Lowry bases are often not Arrhenius bases. And so this is a case where we have a Bronsted-Lowry base, but it is not an Arrhenius base. Not Arrhenius base. And so that's just something to note and remember here. The NH3 does increase the concentration of OH minus in solution because it steals a hydrogen from a water molecule, which then leaves the OH minus. But it doesn't have an OH minus to start with, so it is not an Arrhenius base. Moving on to our next problem, we have sodium hydroxide reacting with water. And so this is a case where we do have an Arrhenius base, but it's actually not a Bronsted-Lowry base. So NaOH, what it's going to do when it gets in water is it's just going to break up. It's going to dissociate to produce sodium, which is then going to have a +1 charge, and to produce hydroxide, which will have a -1 charge. And so the water, while it is necessary to make these ions in aqueous solution, it doesn't really participate in the dissociation process of Na and OH. It's not really the thing that's adding ions to the solution. We're still going to end up with H2O on the other side. The thing that is adding the hydroxide ions is the Arrhenius base, the sodium hydroxide. It is due to the dissociation of sodium hydroxide that we have a solution that is basic. And so there is no conjugate acid and conjugate base in this problem because sodium hydroxide is just breaking up. It's not interacting with the water to make it a base. So all we're going to do here is we're going to highlight the species affecting the pH, which of course is the hydroxide over here on the right side of our arrow. Okay, moving on to number 4, we have C5H5N. So here we have an organic compound, a carbon-containing compound that also contains nitrogen. And so we know that these are often bases. So this substance is going to act as our base, which makes water act as our acid. So an acid is going to donate the proton to the base. So I'm going to show that a hydrogen is being donated over to my base, and we're going to end up with just OH minus left because the hydrogen is taken away from the H2O. And then we're going to end up with an extra hydrogen over here on the C5H5N. C5H5N. And then I'm going to add a hydrogen onto the end. And since this was neutral and I added an extra positively charged thing, this is going to end up with a +1 charge. So now we just need to highlight the conjugate acid and conjugate base. So our OH minus can now behave as a base. It can receive a proton, so this is the conjugate base. And then our C5H5NH plus will behave as an acid and could donate that proton to the OH minus. So there is our conjugate acid. And then finally, we just need to highlight the species affecting the pH, which is the OH minus, the hydroxide. So I'm just going to box that in, really highlight that to make sure we know that that is what is affecting the pH of our solution. And I just realized we did not label the acid and the base in this final problem. This is the base, and water would have to be the acid by a process of elimination. And then number 5, we have HCOOH. And so this one's a little kind of funky looking, but anytime we have a COOH, this is something, a special kind of acid. It's called a carboxylic acid. And so the H on one of the ends is just going to come off and be donated. So we know this is going to behave as the acid, and that means that water is going to behave as our base. So over here, a hydrogen is going to be given up and given to the H2O. That will cause us to have H3O, and because there's an extra hydrogen, we're going to end up with a positive charge. And then because a hydrogen is being taken away, we're left with HCOO, and then we have a negative charge because this acid has lost that hydrogen and lost that positive charge. Now we need to label our conjugate acid and our conjugate base. H3O plus now has a hydrogen that it could donate back to the HCOO minus, making this the conjugate acid. And then HCOO minus now has a negative charge and could accept a hydrogen, making it the conjugate base. Now we're going to highlight the species affecting the pH, which of course is the H3O plus. I'm going to highlight that really well so we can see it really well. Let me fix that, put an E on the end of that word. Up next we have NH4OH, and this is quite clearly a base because it has an OH on the end. This means that it's an Arrhenius base because all it has to do is dissociate to increase the concentration of hydroxide ions in solution. So NH4OH is going to be our base, and by process of elimination, water is going to be our acid. So then here, once again, we have 3 blanks because water's not really participating in this process here. The NH4 is going to dissociate from the OH. NH4 is going to end up with a positive 1 charge, and OH has a minus 1 charge. And then the water is just kind of spectating. It's not really participating. It's just there so that the NH4 and the OH dissociate from one another. So we don't have a conjugate acid or a conjugate base in this problem once again. So all we need to do is highlight the species affecting the pH of the solution, which of course is our OH minus. Next we have HCN, which is called cyanic acid, and of course we know it's an acid because it starts with hydrogen. So we're going to have an acid. Water, our amphoteric substance, will behave as our base. Our acid is going to donate a hydrogen, a proton, to our water, and so we're going to end up with water gaining an extra hydrogen. So we're going to have H3O. And because we gained an extra positive charge, we're going to have a +1 charge on our H3O. And then all that's left of our HCN is going to be the Cn minus, the cyanide portion. So now we just need to label our conjugates here. So H3O plus, or the hydronium ion, now has a hydrogen to donate. So this is our conjugate acid. It's now behaving as an acid. And cyanide has a negative charge and could now accept a proton quite easily, making it the conjugate base. Then finally, let's highlight the species affecting the pH, which of course is the H3O plus, the hydronium ion here. Up next we have HS minus plus H2O. So this actually is a sort of tricky one because you look at it and you say, okay, well there's a hydrogen. The hydrogen could be donated to the water, and technically that is correct. But more likely what is going to happen is that the HS with a negative charge is going to accept a proton. And this is in an equilibrium state, meaning that it really happens in both directions. But here, because we have this negative sign, we're going to assume that water is behaving as the acid, and the HS with the negative sign wants to gain a proton and become neutrally charged. So HS minus is going to behave as the base. And so proton being donated, so we end up with just OH minus because H2O lost that proton, and then we end up with H2S. which is now a neutral substance. So if we assume this is what happens, then our conjugate acid is going to be the H2S because now it has several protons it could donate, and our conjugate base will be the OH minus. But technically it is correct to do this problem the other way as well. So let's look at that too. So I'm going to redo number 8 here at the bottom. Number 8, we have HS minus plus H2O, which gives us two different things. And let's look at it if we assume instead of behaving as a base, we say that HS minus is going to behave as an acid, because it could behave as an acid. It has a hydrogen ion to donate. So if HS minus behaves as an acid, it donates its hydrogen to the water. So we end up with H3O, which of course will have a positive 1 charge. And then all that's left is sulfur, but now since it's lost another hydrogen, it has a negative 2 charge, 2 minus charge. And so in this case, HS is behaving as the acid, and H2O is behaving as the base. So on the other side of our equation, our H3O plus is going to be our conjugate acid, because it now certainly would have to behave as the acid. It would have to donate a hydrogen. Sulfur can't donate any more hydrogens, which makes S2 minus our conjugate base. So either way you do this problem is correct, because both things could happen, but you must make sure that whatever you label as your acid and base, that you label your conjugates correctly as well. And of course here, the substance affecting our pH would be the H3O+. In reality, both of these things are happening all at once quite quickly, and so we're looking at a sort of equilibrium portion where some is H2O, some of our acid is HS minus, some is H2 minus, or H2S, and some is S2 minus, and all of these things exist together. Let's get back on task. Let's look at number 9. We have CCl3COOH. And so we once again have the COOH portion. That's called a carboxylic acid. And so this means that this is certainly our acid substance, which makes water our base. If this is our acid, we're going to donate a hydrogen from the acid and give it to the base. So then we're going to end up with H3O with a positive 1 charge, and we end up with this substance minus the hydrogen. So CCl3COO, and because we lost that hydrogen, now we have a negative 1 charge. To label our conjugates, H3O plus now can behave as an acid because it has an extra hydrogen to donate, so this is our conjugate acid. And CCl3COO minus has to now behave as a base because there are no hydrogens left to donate, so this is our conjugate base. And then finally, let's highlight the substance that affects the pH, which of course is the H3O plus. And then we forgot to do that up here, so let's go back. The substance affecting our pH, of course, is going to be the OH minus. Okay. And then our very last problem, number 10, we have CH3N. So we have a carbon-containing compound, an organic molecule, that also contains nitrogen. So we know that this is going to act as a base, which makes water our acid. That means water is going to donate a hydrogen over to the base. So we end up with just OH minus left over. And then we end up with CH3. We have 3 of those in, and then we end up with an extra H tacked on the end here. So once this happens, we know that OH minus has to be our base because it already has a negative charge. This is our conjugate base, conjugate base. And then over here, our CH3,3NH is going to be our conjugate acid. Now it has an extra hydrogen, it could donate back to the base. So this is another case here where we have a base that does not contain an OH group, but it behaves as a base because of its ability to accept a hydrogen. So right here in number 10, we have another example where this is a Bronsted-Lowry base, but it is not Arrhenius base. Not Arrhenius base. Just important things to note so you can distinguish these later. And then finally, let's highlight the substance that affects the pH, which of course is our OH minus.